Okay. Philip, just one quick question before we begin. Are you okay with the meeting getting recorded so that we can post it on YouTube later?
Yes, I'm okay with that.
Perfect. All right. In that case, let us get started. So it is my pleasure to introduce Philipp Sibbel from the University of Münster, and he will be giving an introduction to Cartan subalgebras. Take it away, Philipp.
Yes. Hi, everyone. Thank you very much for having me or giving me this opportunity, and I wish you a lot of fun with Shanshan later. And yeah, let me give you an introduction to Cartan's subalgebras to set the stage for at least one of the main topics that are in the title of Shanshan's talk. And yeah, let me start off right away with the definition of a Cartan subalgebra. And that is due to Renault building on work of Kumjan. And yeah, here we go. A be a C-star algebra. Then we consider an abelian subalgebra. Call this D and A. And this is called the Cartan algebra. If the following things are satisfied. So we want that D contains an approximate unit. I mean, of course, for itself, as it's a C-star algebra, but also an approximate unit of A. Furthermore, we want that it is maximal abelian. It's a maximal abelian star subalgebra or subalgebra. And furthermore, we want that the set of normalizers, these are all the elements N and A that conjugate the maximal abelian subalgebra D back to itself. So n star dn and also n d n star both lies back in D again. And these elements, which are called normalizers, they are supposed to generate A. As a C-star algebra. Yeah, so these elements n, they are called, I mean, this is supposed to be an n. I'm sorry, my handwriting is not the best, but I hope you can live with that for at least for this half an hour. And this property is usually called regularity. And the third thing that it's supposed to satisfy it is that there exists a faithful conditional expectation of A onto D. So maybe to clarify that, conditional expectation. So that means that maybe call this E. So that's a completely positive and contractive map that's going from A to D. In particular, it is just the identity on D, and also it's linear. So if we take like an element from D, an element from so D1 and D2 and D, and A in A, then we can pull out the elements from D. And faithful, that means that it's that if a positive element, so some A star A, is mapped to 0, then it must have been 0 already. so injectivity on the positive cone basically. And yeah, then this is what a Cartan subalgebra is. That's the definition due to Renault. And like I said, I haven't said it yet, but he was working on this grounds and building on work of Kumjan, who also studied particular massas in C-star algebras, and he studied so-called C-star diagonals. So let me include that as well. That D is called a C-star diagonal if, moreover, all these properties are satisfied, but moreover, the unique extension property is satisfied. So that means that every pure state on D so pure state on D is an abelian C-star algebra, so it's a pure state is a character. It's a point evaluation, and that always extends to a state on a bigger algebra, so on A. But in particular, we want it to extend uniquely to a state, and then necessarily a pure state on A. And yeah, that was introduced by Kumjan. And let me give you a couple more remarks here. So that's a notion that originally comes from the world of von Neumann algebra and was studied there intensively by Feldman and Moore, and yeah, was then translated by Kumjan and Renault into the world of C-star algebras. And it is by now that this zeroth or the very first uh, property is automatically satisfied. That's due to pits. So I mean, in a unital case, that's completely clear because if it's maximal abelian, then it must contain the unit. But also in the non-unital case, that's automatically satisfied. And I would like you to think of these as like particularly well-behaved massas in a C-star algebra. And maybe let me give you the very prototypical examples. So the very first one and very easy one is just in the matrix algebra, n times n, these you can consider the subalgebra of diagonal matrices, and these form a massa, which is like easy to check. Then you have that these matrix units Eij, they satisfy this property, so they are normalizers. In particular, they generate the matrix algebra. And the faithful conditional expectation is given by just deleting everything off diagonal and just keeping the diagonal entries. Yeah, and one can check that the pure state extension property is satisfied. One can check that by hand. That's yeah, probably not too surprising that these are like the prototypical examples. And yeah, that's not only the case for uh, yeah, the simple matrix algebras, but also if you take infinite tensor products of that, so consider the UHF algebra of type n infinity, and then consider the subalgebra generated by all the diagonal matrices. And this also is a Cartan subalgebra with the pure state extension property. So these are C-star diagonals. All right, so the easiest example, and one can really think of these subalgebras as sitting nicely diagonally inside the ambient C-star algebra. Okay, maybe coming to a bit more interesting example. So let's take a discrete group and let's take a space, second countable, take it yeah, compact for now and Hausdorff. And then we want that G acts on X freely or topologically freely via homeomorphisms. And yeah, then one can consider the cross product construction, the reduced cross product in particular, and that contains a canonical subalgebra, continuous functions on our space X. And this is a C-star diagonal if the action is free, so if there are no fixed points at all, and if the action is topological. So in this case, that corresponds to the points with trivial stabilizers being dense in X. Under that milder assumption, this is a Cartan subalgebra. All right, so maybe give you some more clarification. Why is that? So one gets the conditional expectation from the cross product picture directly, and then it's yeah, one can easily see and easily check that the unitaries coming from the group G, that they are normalizers and also C of X itself, of course, and then these generate the whole cross product. And then one need the topologically freeness in order to get that C of X as a massa. And if it's free on the nose, then we even get the pure state extension property. All right, that's the yeah first real example, maybe like going beyond the matrix algebras. And I would like to give you one more example, and that is in the world of groupoids. So giving you right away the subalgebra, and here G denotes second countable as well. Topologically principal groupoid, do that here. We always want the groupoid to be locally compact and Hausdorff, so abbreviate that with LCH. And etal, then this is a C-star diagonal again, or a Cartan subalgebra in the case of topological principality. I'll come to that in a sec. Just want to write it down first. So if you're not familiar with groupoids, then it's probably I think it's easiest to think about it as a generalization of a group where you have a product as well, but that's only partially defined. And as a consequence, you get more than just one unit, but you can get a whole space, and in particular a locally compact Hausdorff space. This is denoted by this G naught here, and then the continuous functions on this unit space, they nicely sit inside the reduced C-star algebra of the groupoid, which in turn is just generalization of the group C-star algebra then. And yeah, that includes a lot of examples for C-star algebras, in particular the example we had before for cross product. That's also a groupoid C-star algebra. And let me add here that we like always want the groupoid to be locally compact Hausdorff. That's like a standard assumption. Then we include the assumption of second countability, just in order to have a nice and separable groupoid algebra. Then the groupoid being L, that corresponds to the group being discrete. It's the analog of a discrete group in the groupoid world then. And then this topologically principality, or the principality on the nose here, that corresponds to the freeness or the topologically freeness in the previous example. Yeah, I don't want to go too much into detail here, but wanted to write that down because this is like the most important example in this case, because it really almost covers all the examples. I think yeah, that let me come to that. But before that, I wanted to say that you will probably see groupoids also in Shanshan's talk. I'm not so sure, but if you talk about graphs, groupoid models are always present. So I assume Shanshan would say a couple more things about that. But let me tell you why this is actually, um, or this actually covers almost all examples, and that is a yeah, impressive result and impressive theorem by Renault, again building on work of Kumjan. And the result is the following. So if you take the reduced C-star algebra of a groupoid, again, assume it to be second countable, topologically principal, locally compact Hausdorff, and Etal. So the same words we had in the example above. And we furthermore allow it to be twisted. So I don't want to go into detail here, but if you're familiar with like twist by a co-cycle or something like that, it's a bit more general. And if we consider the reduced C-star algebra of this groupoid, then this contains a Cartan subalgebra. And again, it's the canonical subalgebra corresponding to the continuous functions on the unit space G naught, like in the example we had above. And the more intriguing part of this theorem is actually that every Cartan subalgebra arises in that fashion, and that's like the opposite direction. So really, every Cartan subalgebra in C-star algebra now arises in that way and arises uniquely. So the groupoid with the twist is unique. And in particular, one can even see whether it's a C-star diagonal or not. So if the pure state extension property is also satisfied or not, and that can be witnessed again on the groupoid level already. So it is a C-star diagonal precisely when the groupoid is principal. And yeah, so the Cartan pair, so the pair of Cartan subalgebra and ambient C-star algebra really completely remembers the groupoid and the twist, so remembers the twisted groupoid, and one can get such a twisted groupoid for every Cartan subalgebra. And we can even, or one can omit the assumption of being second countable here and separable here. Then one need to adjust the notion of topological principality, but I wanted to stick with this original result by Renault. And it's really yeah, I think a nice and important result because it really gives you the chance to study the same object from two different angles. From one side on the C-star algebraic side, working in the C-star algebraic world, and on the other hand, one can really use the groupoids to tackle questions about type algebras from that side. And really, groupoids always have this dynamical flavor. So this theorem really gives you a nice bridge between dynamics and C-star algebras. All right, that's the theorem by Renault, and probably also why interest in Cartans then sparked and got bigger and bigger. And I would like to tell you another really nice and important theorem why that says why Cartan subalgebras are of interest. And that's a theorem that goes back to 2 and then adjusted by Balak and Lee. And that says that if we have a separable and nuclear C-star algebra, which has a Cartan subalgebra, then this C-star algebra A satisfies the UCT, so the universal coefficient theorem. And I don't want to talk too much about the UCT, but it's this big assumption that's needed for the classification theorem. So the classification theorem says that one can classify unital, simple, separable, nuclear C-star algebras that are Z-stable and satisfy the UCT by their K-theory and by their traces. And the UCT is an important technical assumption that is needed and that allows you to access K-theory from KK theory. And it's still a major open question whether all separable nuclear C-star algebras satisfy the UCT. And potentially this world of Cartan subalgebras could give you a way of tackling this question or maybe solving it in the end. And let me mention that two first proved this theorem for or showed that groupoid C-star algebras or amenable nice groupoid C-star algebras satisfy the UCT. And Balak and Lee then showed that this also holds for twisted groupoid C-star algebras. And then in combination with Renault's theorem, which says that if a C-star algebra contains a Cartan subalgebra, then it has a groupoid model. That is this theorem. Okay, so probably the two maybe not most important but very important theorems and an explanation why there's interest in Cartan subalgebras. And lastly, I would like to give you at least a couple existence results in the last 5 minutes. And the first one is due to Spielberg and says that if you take UCT Kirchberg algebra, so simple, separable, nuclear, and purely infinite, C-star algebra that furthermore satisfies the UCT, then UCT Kirchberg, I wanted to write algebras here, that these contain Cartan subalgebras. That is due to Spielberg, who constructed groupoid models or graph-based models basically for Kirchberg algebras, and they are yeah he doesn't need a twist, so the group point model for these Cartans is actually untwisted or like with a trivial twist, and these models are usually not principal. So in particular, these are really Cartan subalgebras and not C-star diagonals. And Spielberg did this basically for the stable case for non-unital Kirchberg algebras, and then the unital case was later resolved by several authors or groups of authors. So that's the purely infinite side, and then if you go to classifiable, so I include that as well. So unital, simple, separable, nuclear, and Z stable C-star algebras that also satisfy the UCT and are stably finite. Then they contain also Cartan subalgebras that are even C-star diagonals, so that satisfy the pure state extension property. So that is due to Shin-Lee. And there's this dichotomy among classifiable C-star algebras. So either they are purely infinite, so fall in the first category here, or they are stably finite and fall in the second category. So in particular, every classifiable C-star algebra contains a Cartan subalgebra and contains or has a group point model, potentially twisted group point model. And for UCT Kirchberg algebras, we know that the twisted group point model can be chosen that with a trivial twist, so without twist, but then the group point is topologically principal and not principal on the nose in general. While for stably finite C-star algebras, the twist is actually needed and necessary and not clear whether that can be removed or not. But we can get principal group point models, so even C-star diagonals. And there are a lot more existence results and also uniqueness or non-uniqueness results outside the space of or outside the classifiable setting. But we have 1 more minute left, or no, now not anymore. But just Shanshan said I'm allowed to say one sentence about my personal research, and that mainly revolves right now around the question whether UCT Kirchberg algebras contain Cartan subalgebras that actually do satisfy the pure state extension properties, so actually whether they contain C-star diagonals or not. And yeah, I think the time's up. Thank you, everyone.
Thank you, Philip. Are there any questions from the audience?
Excuse me, if you go up, please, for the Renault results. Then you say that the reduced, okay, but then this topologically principal means just for the groupoid, not for the twist. Because you have a groupoid and a twist on it.
Yes.
So this topological principle, you just means that the topological principles of the groupoid.
Yes, the groupoid is topological principle or not.
So,
Yes.
but in principle, you don't have any conditions on the twist. Just all the conditions are the groupoid.
Yes, yes, on the groupoid, yes.
Okay. Okay, thank you.
I'm not an expert on twists and so on, but they always seem a bit sketchy
Yes.
to me. But yes, as far as I understand, yes.
Yes, all of these conditions are on the groupoid.
Yes.
Yes. Thank you.
Other questions?
Is it okay? Yeah. So outside of this classifiable setting, like Bilson algebras or these algebras of Andrew Thoms or Mikhail Rodum, do these also, are these known to have Cartan subalgebras?
I don't know. I'm sorry. haven't looked
Yeah.
into that. Maybe someone else knows. I don't know. Sorry.
Okay. Karen thinks so. Karen thinks yes by Alirad and Shinley, but yeah. Anyway.
Okay. Nice.
Thanks.
Yeah. I think, yeah.
Any other questions?
Yeah, I would just really like to say that for talk.
Thanks.
Yeah, but before that, maybe make sure that if there are any questions from the online audience, I would also like to give them a chance to ask any questions. If not, then let us indeed thank Philipp once again for his time.
Thanks.
Right. And then we will take a 10-minute break and we'll be back with Shan Shan's talk.